Yeah, those are the tips. I also got a little lucky with truck rides. I got a little lucky with weather, you know. But if you show up like you all do, that also do the FAA to be qualified as a check instructor.
You one.
Nope.
Okay.
No, I was 61 student. I am a 141 instructor, but then there's sort of like the next level, which is not next level, but like, you know, in order to do like check ride. Morning, Wayne. Morning. Eventually, once we get 10 people from each 141 course to pass a check ride through 141, then we can apply to the FAA to do our own examining, which means that your check ride is your final phase. Your final phase check becomes your check ride. Yeah. You just go with Paul or Jimbo or Eric. Yeah. This is what I'm saying, people. Like, we need to, and this is why you get priority for a check ride now, because we don't yet have the examination authority. But once we do, once we get 10 people, it's per course. So 10 141 instrument, 10 141 private, 10 141 multi, etc. But once we get 10, we can apply to the FAA and say, we've proven ourselves now, let us do the examining ourselves. And then your final phase check is your check. You actually fill out an IACRA for your final phase check. And then Paul shakes your hand at the end and gives you your cert. Yeah.
Just go for me.
Yeah. In fact, and skip instrument, just go straight to, and skip commercial single, just straight to commercial multi.
That's what this commercial event is for.
Yeah, except you can't, no airline's gonna hire you without your instrument. Because all 131 and 135 and 121 is flying with instrument. Sorry about that. Good morning. I'm so surprised. We have no Paul. We have Erica in the flesh, so not online. Nobody on the internet this morning. That's okay. I'm glad to see you all this morning. It's Thursday, but feels like Friday. The warm-up is on the board. Today's weather. So here's the warm-up. Pull up the current surface analysis chart. Where are two places you could find that? For flight imagery and aviationweather.gov. You totally can, Moon. Like it won't bother me.
You pull up it.
It's fine. It's fine. Let's mark you down here.
My integrity limit.
Hey, good morning, Chris. Buenos dias. So pull up the surface analysis chart, current one, for flight imagery, aviationweather.gov, both good spots. And then what we're gonna start with is just noting some of the notable weather conditions that are existing right now in the lower 48. That's gonna be our warm-up. Or for flight imagery, they both have free. You know where to find it for flight imagery? Sure. It'll take a couple minutes and then let's go. Imagery tab. No, actually under more. There's a whole mess of not just whole resources. What's that? Yeah, the whole country, yeah. Because where we are might not be that interesting. Steven's got all these charts. This is all from aviationweather.gov. But you press the latest surface analysis, that's the surface analysis chart. Yeah.
Wait. There's a question just kind of. Should I contact? No. Just find something off that, off the lines.
If like you've done something wrong and you stay outside from. We're gonna close the door on you. And
Oh, Discover Weekly playlist has been so good this week.
rare.
Really? I've got the sucker trained. In some weeks it just hits. This week, oh,
You have spot. Upwards and then outside.
AWC, there we go. All right, team. Good morning. Welcome. It's just us. I'm worried. Am I on the wrong Zoom? Like, what's happening here? This is the first day ever that no one has joined online.
Paul usually is on.
Paul's on, or there's always at least one or two people who are on. Interesting. Okay, well, we're gonna start anyway. Today is the last day of new content for week 2. This is the first week of real sort of like IFR content, right? With last week being a lot of private pilot review stuff. Here's the plan for today. The slides have a lot of really good private pilot weather theory review. I have decided that we are not going to labor over those as a group. Instead, I'm going to leave those for you to review mostly on your own, because what I want to prioritize together is some stuff that's not in the slides yet, but that will be for I think the next round for folks who come back in the with the August class on icing, because the most likely topic to come up on weather in your IFR check ride is icing. In fact, I would be shocked if icing does not come up. So with your permission, and well, actually, I'm not actually, I just decided this. With my apologies, we're not going to go deep on weather theory today. If you'd like to go deep into some of the weather theory during review week, which is week 5, you can nominate a topic, we'll put it on the board, we will cover it together. But the slides will be there for you to review. So the only part of weather theory that we're going to do is this warm up. So we're going to look at the surface analysis chart together. That'll be our sort of like, we'll get some of the big picture weather theory. Then we're going to talk about icing. Hope that'll leave about 40 minutes at the end of class for us to return to the content from yesterday. Because we talked about a lot yesterday with departures, and there's a whole phase check on departures. And the slides yesterday were brand new and gorgeous, and I'm still so happy about them. But I would like to do some more practice on departure procedures and standard and non-standard departure minimums, both for performance and visibility, and really hammer that home, especially because we're off tomorrow. I normally do that tomorrow on review day, but we don't have tomorrow as a review day. That's the plan. Sound okay? Cool. All right, so surface analysis chart. There's a couple of places we can find it. As we mentioned, one is in ForeFlight imagery, and the other is AWC. If you're using AWC, what's great about AWC is when you first log in, it literally tells you in highlights sort of like, hey, there's some stuff going on in certain areas. So all of the red and magenta circles are airports that are reporting IFR or low IFR. So right away, just literally on the homepage of AWC, I'm like, all right, there's some West Coast California, some kind of visibility issues or ceiling issues. I'm also seeing some PIREPs, right, in various places. And I'm seeing some kind of either airmets or sigmets, these like red polygons. So automatically, if I was say going from like I don't know, Idaho Falls to Butte, I'd be like, all right, well, maybe there's not something super major. But if I was going from San Francisco to Santa Fe, I'd be like, all right, I'm flying through, I'm leaving IFR, there's some kind of turbulence pyre up here. I don't know what this is. Just kind of gives you like an instant shot. Okay, where are my big hazards? Obviously, that does not completely fulfill our requirements under the W and W craft. But sort of like how I say your pre-flight starts the minute you step on the ramp, sometimes you notice things, big things from farther away than up close. Same thing with weather. So it's important to just start with the big picture because when we zoom in, we might miss something big. That's just harder to see when we're zoomed in. I'm going to click on this. It's going to take us to our observations. That's the current observations. This at least tells us our radar, right? It tells us PIREPs. It tells us some weather conditions at airports. It doesn't tell us, though, what the surface analysis chart does. What are we missing from this? Fronts, what else?
High and low pressure.
High and low pressure systems, what else?
Troughs.
Troughs, what else? Isobars, that's what I was looking for. Yeah, all the fronts and isobars. What's an isobar, Moon? Oh, as you take a bite of McMuffin. Yeah.
No, it's equal.
Yeah, ISO meaning the same, and bar is a unit of pressure. So same pressure. So along those lines, you have all the same pressure. If you've hikers in the room, if you use topographic maps, actually this is also the same on the VFR sectional, right? You've got lines of equal altitude. This is now lines of equal pressure. So the way I'm going to get that is
You're on the front on this page.
wait, can I?
Yeah.
Okay, let's see. Here we go in the little like layers tab over here. Looks like a little hamburger, exactly. I can turn on fronts. I can turn off METARs. I can turn off the radar for a second. Is this cool? I can even turn off the sigmets if I want to just really clean this up. I can turn off the PIREPs. Now this is looking more like what's in ForeFlight, right? What was your question, Chris?
What are the things for?
These are some kind of sigmet or airmet. Oh no, it's a gale warning. That's a warning issued for ships. It's a sea-based. It's a shipmet. I don't know what they call it in maritime, but it's a gale warning as high winds in the ocean or on the lakes. That's for ships.
Still be
Still potentially relevant for us if we're coming in from I don't know, into San Francisco from the west. So it's also it's also produced by the National Weather Service. So that's it's presented here. Very interesting. I'm gonna try to clear this. Somebody put in a route. I'm gonna have to clear that. Okay. All right, this looks a little more like it, yeah. And I can actually go back in time, right? To see some trends over time. What is the Zulu time? Those of you who are on ForeFlight, what's the Zulu time of the surface analysis chart that's in ForeFlight?
10.
1410 Zulu, which is what time local?
7. 10.
Yeah. Wait, is it really 1410? That would be a very fresh, I mean, it could be.
7:14.
Right now it's 7:14 a.m. But like what I mean is like, was the chart really issued for observations at 7?
Mine said 10:30.
13:30 is Thursday, July 3rd. No,
That sounds more like it. Let's look.
Oh, yeah, I just got updated.
Yeah, yours is correct. I just wait. Yeah, that's the same. Right. I don't know why this is in night mode. Yours is in day mode. It's probably something in the browser that I don't know how to do, unless somebody isn't over here. I wish there's a way to like press. Does anybody know? Can I press? Oh, here we go. Base map. Light gray. Does that look like more like yours now? That looks a little more like it, huh? Okay. I wish there was a button, and maybe if somebody knows, like, can I just press like reset everything to defaults? Like whatever happened in other classes, we're over it. Okay, so I'm sorry, going back to the original question, what time was the one in Fort Flight valid?
13:30.
Okay, so that's when it was issued. But the top where it says 1200 Zulu service analysis is actually when those observations were made.
Okay.
So it was issued, right? Because obviously somebody has to sit in an office, or maybe a bunch of somebodies sit in an office somewhere at some National Weather Service office. It takes them an hour to put it together. So it's based on observations from what, 1200, you said?
Yeah.
So 1200 is what time local? 5 a.m. local. So I'm just gonna reset mine back here to 5 a.m. That should look similar to
Oh,
yours, yes?
isn't that method kind of like, I don't know what the word is, but I mean, if they're seeing it 1 hour before, can it just all change within that hour that they're?
Not only can it does, right? The weather's constantly changing. So this is the difference between an observation and a forecast. Surface analysis chart is an observation. This is what the weather was. So what the fronts, the pressure, the the isobars, all that, that's what was happening at 1200 Zulu. We're going to talk about the prog chart in a minute, that prognosis chart. Same information as the surface analysis chart, except now it's a forecast. Right? But since it's an observation, they're always same with our METARs, right? METAR is an observation. So there's a gap in time between when the observation is made and when we get that information through an ATIS, or in Fort Flight. Yep, cool. All right, so this is it changed time. This is the 5 a.m. Surface analysis chart. Moon.
Yes, so remember when it was observed was 1200 Zulu?
Yes.
And when it was issued was like hour and 30 minutes?
Yeah.
The reason why there's difference, or is that because it's negligible, like we can just look at that and, okay, that's probably what's happening right now, or?
Probably close, right?
Okay.
But what we're going to do is we're going to use the surface analysis chart in combination with the prog charts to help test that theory, right? To help kind of kick the tires on that theory of like, okay, well, it's now that was at 5 a.m. Now 2 hours later, that's 2 hours plus stale. We're going to kick the tires on the theory. They're like, okay, it's about the same. Yeah. There's certain weather phenomenon that change faster than others, right? For example, if you have a fast moving cold front, if you have thunderstorms, right? These things don't last, they can change quickly. But this generally today, we're experiencing some low pressure in our area. Probably we're still experiencing that low pressure. Since it's not associated with like a moving front or a cold front or something like that. Yeah. So let's talk a little bit about, based on this surface analysis chart, what kinds of major weather phenomenon might we expect? And this is now available for any part of the country. Erica, will you kick us off? Tell us, pick somewhere and tell us what we might expect. Okay, down here. Yeah. Yeah. Yep. Good.
Yes.
Nice. No, this is PPL weather theory review. Yeah. What kind of visibility, what might we expect in a low pressure system? Exactly. That's right. That's right. Yes. Yeah, exactly, right? Because we have that rising action. Anybody remember the definition of stability of the atmosphere? Exactly. So low pressure, it's getting sucked up. So there is vertical motion. That's why we have turbulence, but it's also why we have the visibility, all the dirt, dust, pollutants, they're all getting sort of sucked up and pushed away. Rise up and float away is what my teachers used to say. You used the phrase counterclockwise motion, which is correct in the northern hemisphere. South in the Aussies, they do it differently down south. But up here, counterclockwise, there's a special weather term for that. Anybody remember? Cyclonic, exactly. It's called cyclonic flow, the counterclockwise motion of a low pressure system, which is caused by what other phenomenon in the northern, caused by the same phenomenon in the northern and southern hemisphere. They just move differently in the northern and southern hemisphere. Do you remember what causes it to cycle, to do cyclonic? It's not just a pressure system on its own. It has to do with something else about the Earth's rotation.
So does it,
Does it cause jet stream?
It's the way they.
Yes,
It's heated evenly, right? So heat rises across the equator.
you are correct, right? Like all weather is caused by the uneven heating of the Earth's surface by the sun. What I'm trying to get at is the Coriolis effect, right? The Coriolis effect is what causes this motion of pressure systems. So low pressure cyclonic, counterclockwise in the northern hemisphere, clockwise for high pressure, anticyclonic they called it, which is weird. Why wouldn't it be countercyclonic? Because it's counterclockwise. Anticyclonic. I think maybe in Britain they call it anti-clockwise or something. I don't know. We'd have to ask we'd have to ask Dom. That's the basic things. One more thing about here. What are these dotted yellow lines? Or orangey line, brown lines? Brown lines. A trough, which tell us what's the definition of a trough.
Like.
And I think of it as an area of relative low pressure. So it might not be an absolute low pressure, but compared to the pressure around it, it's an area of relative low pressure. So different than, say, a cold front where we expect certain kinds of weather, which we'll get to in a second. Troughs, they don't necessarily mean bad weather in the same way that like a cold front might, right? We're not necessarily going to get like thunderstorm developments right now if we were to go outside. But they're important for us to know about because they can be associated with some other weather phenomenon, especially in California. This is a very typical California trough, right? Like down the middle of the state. Very typical. Okay, great job. So we've got good visibility, maybe some instability because it's low pressure today. We've got a little bit of a trough. Yeah, that's good. What do we expect our pressure to be? What was our pressure in approximately our area at this time? 1,010 millibars, which is how much in inches of mercury? Sorry, yeah, oh, just kidding. I'm not gonna ask you to do that. What's standard pressure in millibars? 1013.2, I think, right? 1013.2 or something. Yeah, 1013. So if 1013 is standard, that's 2,902 inches of mercury. So do we expect, oh, that makes sense, right? And we're doing kind of a little check. Cool, that's less than standard. 1010. So that makes sense. That's we put the little L here. Well, over here it's already 1007. That's even lower than standard, even so. But up here we're getting closer to standard. Look at this high pressure, right? Relative high pressure. It says H, but it's only 1014. That's like, probably still less than, we could ask Siri to do the conversion for us, I'm sure, but it's my guess is that it's probably less than 30 inches of mercury, or not much more than 30 inches of mercury. Oh, all right. Thank you, Erica. Well done. Let's move on to another part of the country. Jacob, pick another area and tell us about the weather, please. Major weather phenomenon.
You're looking at area.
Yeah. Anybody from New York? Any East Coasters? Amazing. Amazing. My life is filled with New Yorkers, ex-New Yorkers. So this is what a pleasure to be with you. Okay. Yeah.
See the big cold front coming in from.
You're talking about this?
Yes.
This Canadian cold front? Okay.
And there's two signals, right?
Ooh, was that showing on your surface analysis chart or did you turn on a layer?
Signals.
Okay, so we can turn on SIGMETs here. This is where the functionality of aviationweather.gov exceeds the static image in ForeFlight. Static image in ForeFlight is legal, right? But again, there's a difference between. It may not be. It doesn't have the same functionality. One can just be like, cool, let's turn on fronts, or let's turn on SIGMETs. Let's turn on center weather advisories. Let's turn on the gale warnings. Let's turn on air mets. Wow, and I can even pick which kinds of air mets I want to put. Right? There's like a lot of functionality here that we can just click on. So here you've already turned on the SIGMETs. Wow, convective SIGMET. How long is a convective SIGMET good for? When it's issued?
2 hours.
2 hours. 2 hours. They're like a short-lived SIGMET. They can be renewed, but they are short-lived. Convective. Yeah, go ahead.
The way I think about it is it goes down. So airmint is 6, and then when the convective SIGMET
Convective segments too.
Right, too.
Yeah, mountain obscuration. Those have standard times, they might. We have to look into that.
Doesn't that count as a airman?
It's an air met, not a sigmet, you're right.
Yeah, so.
Air met, 50 hours.
And then it goes
Yes.
back to segments, which is 4 hours.
Yeah, but it's for like specific things like dust storms or like volcanic ash or something.
That sounds right, that sounds right. Where would we find the answer to this information? What FAA publication?
What, some legend, I don't know.
May not be a legend, I don't think that's in a legend. But there's PHAC, it might be in the PHAC. Did you know, little known fact that we're gonna explore today, did you know there's an entire weather handbook that the FAA publishes? There's a whole, I know, but they're all in your ForeFlight already, which is amazing. If you go to Documents FAA Handbook, the Aviation Weather Handbook is delightful reading. I just think like if you're a weather nerd, or even if you're not, because we have to be a little bit of weather nerds to be pilots, it's amazing. So that tells you everything about all the weather, including things like, okay, how long is this air mat or this SIGMAT or what have you. So definitely be in the Aviation Weather Handbook. Yeah, it's good times. It's good times. Let's decode this real quick. Let's just look at the raw data here. This is what KKCI. Can I zoom in at all? I can't. Good. Anybody can answer.
The airport?
Nearest airport, just like in a PIREP. What's this?
You might zoom in.
A little more? Let's see what I can do.
There we go.
Okay, great.
I'm not blind, it's the TV.
I'm calling your AME. I'm gonna demand an eye exam at your next medical. What does this mean? Date? Decode it for us, Jacob. Yep. Exactly, great. Sigmet, convective sigmet, 92 echo. 92 echo is like the, I guess, the identifier for this particular convective sigmet. When is it valid until? Has it expired yet? What time is it? Oh no,
Expires in.
Yeah.
15:57. Right now it's 14:27, so it's still got another hour and a half. Maine, Massachusetts, New Hampshire, Vermont, and New York.
That's all the state that affects.
Correct. From 70 degrees
West, northwest.
west, that does not make any sense.
The western part of. But that's 070.
They do that on Britain. It'll be like north. I'm like,
The good news is I don't think there are any questions about decoding a raw data SIGMET on any written, nor have I ever heard of a DP making you do it. What this is telling us are the boundaries of the SIGMET. Thank goodness we have graphical representation on AWC and on ForeFlight, so we can just look at the map. But this is in writing, I believe, the actual corners, so you can draw the shape of the SIGMET.
Maybe that's the distance
Is
from the
that-
airport.
Fair.
Yeah. Oh, maybe that's a VOR. Maybe that's a VOR. Maybe this is a VOR. That's possible. That's possible. That's a good theory. I'm into it. And here's the real nut. Here's the real meat of it, right? Area of thunderstorms moving from 240 at 15 knots. Tops to flight level 380. Damn, those are some high clouds. Those are some big old towering cumulonimbus. From 24015 knots. All right, I should have boned up on this a little bit, so I apologize. Just press the decode button on ForeFlight, and it'll tell you. Bottom line is, are we flying into a convective SIGMET?
No.
No, definitely not. Okay, back to you, Jacob. Tell us more about the kinds of weather we might expect in this area.
Since it's gonna be a lot.
Bad weather, cold front. Yep. Cold fronts move relatively, as compared to warm fronts, fast or slow. Typically fast. Yeah, tell us a little bit more about cold fronts, like, and how the air moves through. Like, I think about, like, is it pushing under or is it going over the top?
Pushing.
Yes, it's like a snowplow. That's how I was taught it, right? Like cold fronts, because the cold air sinks, right? So when it's pushing the warmer out, it's kind of like a wedge, a snowplow pushing that warmer air up. That's what's causing the convective activity. And it's very common to see convection in front of a moving cold front because, and sometimes that's even called a squall line when there's a nice thick line of bad weather, precipitation, thunderstorms. What are the three things we need for thunderstorms?
Visible moisture, uplifting action.
Correct. Yep. Unstable atmosphere, which means unstable atmosphere, right? Well, this action of the snowplow is doing at least one of those for us by pushing all of that warm air up. Rising action. That's what's happening there. So if we've got visible moisture and some other instability, boom. Visible moisture and instability, then we've got thunderstorms. And that's what's happening here. So even before we turned on the SIGMETs, right, we know from our weather theory knowledge, probably not a great time to be flying general aviation in the Northeast this morning. Probably not a great time. Probably not a great time. Yeah. Tell us about this front, Jacob, this part.
It's stationary.
Yeah. Talk to us about what the stationary front is.
That's cold. Hit each other.
Yeah, this is like this is like two equal teams, head to head. Sorry, the sports metaphor is not coming to me this morning in this moment, but it's
Two linemen hit each other.
there we go. Thank you. Great. Thanks, Jacob. Appreciate it. Wow, 2 days in a row with football references. It's gotta be a record for my class. Great. We love it. We love it. Cool. And we've got another stationary front down here, right? This cold front's right on the heels of this other cold front. This is a bad day on the East Coast and the Northeast for us to be flying GA. Cool. Nicely done. Chris, let's move to you. Pick an area and tell us where some of the weather, what weather you're noticing.
Up in.
Oh, you're talking about this one? Yep.
That's right. Yeah.
This is Oregon, this is Washington, Idaho. Well, it's funny because actually on the written, they actually have some questions.
Yeah.
Have to know geography. I'm like, is this literally high school geography class or is this an FA written? It's so frustrating.
Everything
That's right. That's right. You got to know where Tennessee is to be a pilot. Right.
It's part.
I'm telling you.
Also, I know what Texas looks like.
You're such a Californian. The poor flyover states. Anybody from the central part of the US? No. There we go. That's what's up. That's right. Not Minnetonka. I made that joke earlier this week too. That's right. Remind me what part? Where'd you grow up?
If you zoom in, see far.
That's Wisconsin. Wait a second. Here's
the left.
there's Minnesota. St. Cloud, Minneapolis.
No, west. Go. Yeah, Fergus Falls.
Hey, you were right on the front today.
Yeah.
Nice. Wait, what airport do you fly out of? You're not near any major airport.
I would either drive 4 hours down to or Fargo has a Delta. It's also
Does SkyWest fly to Fargo? That sounds like somewhere SkyWest would fly.
sure about the airline
Or PSA or GoJet or some other region that we're gonna fly on one day. Fargo has a Tersa? Cool. Little known fact. Heard it here first. Anyway, that's good. All right, Chris. So you've got another cold front here. Good. Let's talk about this purple situation up here in Quebec. Yeah, go. Tell us what an occluded frame is.
included the cold front takes over though.
Yeah, faster moving cold front overtakes a slower moving warm front and kind of merges. Good weather, bad weather, or weather.
And it kind of makes sense they made it purple because cold fronts are blue and then warm fronts are red.
Yeah, they do have our back. So what kind of weather? Good, bad, or There's only one answer. There's only one right answer.
Yeah.
Think about it, okay? If you had like a bunch of,
Well, I want to.
if you have a bunch of cold water and a bunch of hot water and you pour them together, it does in fact make it lukewarm, just like purple, but there's going to be a lot of stirring up, right? And a lot of steam and a lot of problems as those two conflicting air masses, right? Or in this case, water masses mix together.
So bad.
Bad weather. Similar to a cold front, but potentially.
So in that case, it's like, because you said a cold front is like a snow plow.
Yes,
If included is the same, is like cold front taking over warm front, it's a big snow plow.
sure. That's actually a good way of thinking about it that I hadn't thought of before, but yes, exactly. Warm front is like a blanket, right? It like lays on top of the colder air mass. Still can cause issues, right? Because that air is still going to want to circulate and get together, but not quite as bad as that snow plow of the cold air pushing up that warm air. Also, warm air can hold more moisture. Let's talk about that for a second, right? There's temperature and dew point. What is dew point? What is the definition of dew point?
When the
Anybody want to give it a shot?
water saturated.
The temperature at which a parcel of air, this is another great FAA weather term, right? A parcel meaning just like a box. If I was to, get a nice parcel, a box, and put air in it, that's called a parcel of air. If I want to, the temperature at which a parcel of air will become fully saturated. So however much moisture is in that parcel of air, if I was to cool it, it would be at that temperature that it would turn into fog, cloud, rain, precip. That's the dew point. It's a measure of how much moisture is in the air. Warmer air can hold more moisture than colder air.
So in that case, the dew point in Toronto right now is 13 Celsius.
Okay,
That
and what's the
means-
temperature?
The temperature is 17.
17/13, okay?
So does that mean if the temperature were to drop to 13 at 17, our relative air would turn into fog?
Fog, cloud, mist, haze, something like that.
Humidity.
Rain. Yeah, so the temperature dew point spread, right? And the dew point actually by itself, but especially the spread, helps give us information about the humidity of the air. It's different than relative humidity. Relative humidity is a percentage of how much more water the air could hold at that given temperature. The dew point is, all right, given this current amount of moisture that's in the air, if I were to cool it, dew point is the temperature at which that parcel of air becomes fully saturated. So you're getting onto something, Chris, and this is what we use most, back in the envelope in aviation is the temperature dew point spread. The closer the temperature and dew point are, the closer that parcel of air is to being fully saturated. And when you're within about 4 or 5 degrees Celsius, that's when you can expect visibility problems. Fog, haze, mist, dew, precip, cloud, right? That's when the temperature dew point is close.
And it makes sense because right now it's marginal VFR and it's broken at 17.
Exactly, right? And how's the viz?
10.
Okay, so we've at least got good viz. Yeah. But if I was, say, doing a cross-country flight, right? And I was taking off in the afternoon, planning to come back at night, I might look at the trend of the temperature dew point spread as one of my indicators of how likely is it that I might have a visibility problem when I come home, right? If I see that, I know that the temperature, the air is going to cool off when the sun goes down, right? So if that moisture stays the same, which it probably will, barring some other major weather phenomenon, as it marches closer to the dew point, we could have viz problems. And the other way around too. If I'm at home and I'm looking like, oh man, the temperature dew point spread is 3 degrees, but it's the morning and I know it's going to warm up by the time I pre-flight, by the time the sun comes up, that temperature dew point spread is going to clear, and that's why we have burning off some of that haze or other visibility problems. Of course.
Like stationary fronts.
Yeah.
Associated with bad weather. but
Yeah.
it's not associated. Is there?
Yeah.
Like. Yeah, like I know it's really bad weather. Cold front, it's really bad weather.
Yeah.
But a warm front, I don't. To me, it just feels like very like stationary, like blanket or like a pot lid or something like.
You could still have storms, right? You could still have storms with the warm front coming through. You could have turbulence, you could have wind shear, you could have precipitation, you could still have all those things with a warm front. So it's not typically quite as severe and it's not as fast moving as a cold front, typically.
Because like my understanding of
Yeah.
it is like. yeah, like warm air just moves over it, so there's not a lot of uplifting action, so I don't really
You know,
understand.
you might have, if you're traveling through that warm front, as you travel through from the relative colder air into the warmer air, that's where you could get turbulence and potential wind shear, like at the boundary itself.
That little like,
Similar to like when we have a temperature inversion here and we're climbing through the inversion, same idea, right? As I travel through that area where the air is shifting in temperature or wind, that's where I could have some turbulence.
You're referring to stationary front? Or just a
Stationary
warm
front or a warm front, any kind of frontal boundary. Yeah. Doesn't necessarily mean that you, like a cold front in our planes, right? And all of our personal minimums, we're not flying typically through this kind of weather that we saw here, right? Because that's cold front, there was thunderstorms, we have convective signet, we're typically not. You know, the trough, we're all going flying today, I assume, right? Like that's probably not a situation. Up here, well, maybe we have questions about it. Where could I look to be like, okay, I see it's a stationary front. Is that actually going to cause problems for me? What other sources of weather might I look at to answer that question? METARs, what else? TAFs, right? Winds, temperatures, winds aloft, which are forecast. Those are some other sources I could be like, okay, what's really going on there? How does it affect me? I would also recommend, you know, for all the weather theory stuff, the PHAC's great. The aviation weather handbook is even better in more detail. But the PHAC is a great sort of like weather theory. And the slides, to be honest, if you see, where are our slides here from today? There's a lot in here about thunderstorms, cloud types, even starts with like the layers of the atmosphere. There's a lot here. And on week 5, if you want to dive a little more into that, we can. Yeah. Okay. Let's talk a little bit more. I think we've milked this for most of what we can. This, again, was a observation. So let's look into the future. I'm going to switch to a prog chart. You can do this on ForeFlight as well. Prog stands for prognosis, meaning like into the future. What is going to happen in the future? And this starts now here at, this was at 5 a.m. local. And what's nice about aviation weather, they convert it into local time for us. So if you go into imagery, prog charts, you can flip through these same ones. But we can start to see if I sort of like put this forward, it almost animates it for us. You can see, for example, look at this Canadian cold front. Started up here. Watch where it goes. Okay, now New York, this is plus 6 hours, 11 a.m. local. Now we've got situations here through the whole Northeast New England. Then this afternoon, we're starting to get into DC. No, that's actually New York. New York, Vermont, New Jersey, and then plus 18 hours. Now it's mostly past. It's an example of how you can do this for your flight planning. If you don't remember what the colors mean, just click on the legend. So the yellow is fog. This green is rain, chance, or likely, depending on if it's light green or dark green. And then we're going to get into some of our fun stuff here with icing.
what's the difference between chance
Uh-huh.
and likely?
There's an answer for that also in one of our FAA handbooks that I cannot remember. Sorry, I can't remember. But there is a definition for it. Chance is just, it might happen. Likely is like, you could probably count on it happening. It's a measure of how likely the rain is. So chance of rain means like, it might rain. I don't know. I'm sorry, I don't remember the exact percentage. There is a cutoff. Likely is like, okay, it's probably gonna like for sure rain. Oh, not quite for sure, but like it's very likely it will rain. Cool. That's our weather theory overview. Any other questions at this point? We start to talk about icing. Okay. Let's talk about icing, friends, because this is really where our instrument check ride is going to focus when it comes to weather, and also what we as instrument pilots need to really focus on. We can have, when we fly, we are always worried about various kinds of weather phenomena. But when we're flying through clouds, we're especially worried about icing, which is when precipitation hits our airplane and freezes on it. This happens around or below freezing. We can actually get icing on our airplane, even maybe as high as say 5 degrees Celsius above freezing for various reasons we'll talk about in a second. But 5 Celsius or below, at or below freezing, And we're going through visible moisture, that's when we have a risk of icing. So the two ingredients for icing are visible moisture and temperatures at or around, around or below freezing. Those are the two things that can cause icing. In VFR flight, we don't worry about it as much because we're supposed to stay out of the clouds, right? We're not supposed to be in visible moisture. And so we learn a little bit about it in private pilot, mostly, okay, this is what it is, and this is what you do to get out of it. But now we're going to be all expected to know way more about icing because we could be flying and actually are flying through clouds when we're in IFR. So let's talk first about how icing forms. When I'm going through a cloud and its temperature is near or below freezing, water droplets impact the structure of the airplane. This is called structural icing. There's a couple of different kinds of icing. So the first one we'll talk about is structural icing. Just like the name suggests, this is when ice forms on the structure of our airplane. Wings, tailplane, windshield, little temperature probe, pitot tube, whatever is sticking out there. And because of physics, small protuberances and thin things are likely to pick up ice sooner and faster than larger, thicker things. This has to do, I think, with the way water molecules like to stick with each other. So for example, if I have a little pitot tube hanging out here that's like thin and small, that's actually going to get iced faster than like the windshield of my airplane, which is bigger and wider. The tail of my airplane, because it's smaller and thinner than my wing, is going to collect ice sooner than my wing itself and my leading edge of my wing, because this tailplane, right, is thinner and smaller than my wing.
So you can assume if there's ice on your wing, that there's definitely ice on your elevator.
That is correct. That is the whole reason of talking about this theory. Exactly. You can assume that if there's ice on your wing, you've also got ice on your elevator, your vertical stabilizer, rudder, right? Like there's like this, exactly, that your landing gear, all of that, right? Your landing gear is going to pick it up before your windshield. So some airplanes actually have a little icing indicator. It's like a little, it actually looks kind of like an outside air temperature probe. Have you ever looked at you should be in your pre-flight looking at the outside air temperature probe that's stuck in the cabin vent on the left side of the plane, right in here, in this vent, which that's just a vent right into the left side seat. That's sticking out from there on our plane is a little probe. That's our outside air temperature probe. So it's like the same size of that, except they put it like right in front of the pilot's view, like right in the front of the forward windscreen, and actually put a light on it in plane so you can see it even at night. And that's sort of like your early warning, like sacrificial little probe that helps alert the pilots that icing is starting. Because we're taking advantage of the fact that like thin, small things are going to collect ice faster. So if you see icing on your little icing indicator, okay, I know we're in icing conditions. That's what's happening. Yes.
Kind of extension of what Jacob said. So we're expecting structure ice in the smaller surface, such as vertical stabilizer and horizontal stabilizer.
Sure.
As well as wings.
Yeah.
But since our three main accord control, the aileron, rudder, and elevator
Yeah.
are behind the surface,
Yeah.
are we expecting a malfunction of the control? Or is it
You
more like-
could if they freeze shut, but they may not freeze shut.
Okay.
Let's talk about this, for example.
Yeah.
Say we're getting icing. What can we expect to have happen to our airplane?
lift and
Cool. So let's talk about those two things separately. First, we're increasing weight. Why are we increasing weight?
ice on the-
Because we're literally adding ice to the airplane. Exactly, right? We're literally like picking up weight as we go from the ice. So what does that need? What does that require in order for us to stay straight and level? More power and more lift, right? These are connected, and also a higher angle of attack, right? So now we've got a higher angle of attack. We're at full throttle, maybe, right? And we're at a higher angle of attack as we go. What's happening now as we're at a higher angle of attack? What's getting exposed now to the airstream and this precipitation? Bottom side of our wing. So now we're even exacerbating this further, especially now maybe we're even slowing down right? Because like the plane is not able to keep up with, and now we're exposing even more. Even you can see how this can get bad pretty quickly, right? If you're in severe icing and you have either you're in an airplane that's not rated for flight into icing, known icing, or your anti-icing and de-icing systems have become overwhelmed, this is a problem real fast.
Especially with the autopilot.
Right. We'll talk about that in a second. Hold that thought. Then the other thing you said was weight, and you said it disrupts the airflow over the wings.
Yeah.
Right? It decreases our lift. So if I have ice collecting on, say, the leading edge of my wing, now I'm not having that smooth designed airflow to take advantage of Bernoulli's principle to induce lift. So that means what else am I gonna have to do? Same problem, right? More higher angle of attack. This is also going to increase my stall speed, exposing more of my lower wing into the airstream to get more icing in there. Problems. Yeah. Hold the autopilot thought until we talk about what to do if we accidentally encounter icing, because that's going to be really important. Yeah, right. I will too. Okay. So those are the problems we have with icing.
CG.
How would it move my CG back?
If it's forming on your stabilizer, it's adding to it.
Look at that, right? So it's gonna mess not only with my weight, but also potentially with my center of gravity, right? So now I need to if my center of gravity moves back, doing an extreme example here, right? Now I need to, elevator down. I might actually exceed my trim authority or something, right? Like this could be very problematic in terms of being able to keep us nose down. And if our center of gravity gets too far back and exceeds our envelope, stall. That's right. Good. I thought about that, but that's right.
Would you also say that since we're putting a lot of undesired ice on our surface, we're increasing our parasitic drag, the skin friction drag?
Yeah, because there's more rough surface to grab the air. That's actually true. Yeah. So we have to increase our lift. When we increase our lift, we increase our induced drag. But I think you're right. I would agree with that. There's like a rough surface now, potentially, that's also causing more friction with the wind, parasite drag. Yeah, I would agree with that.
Four bad things at the same time.
This is bad news bears, right? And this is why when we're now instrument pilots and we're going through the clouds, this is why in our check rides, I don't really think you're going to get quizzed. I haven't heard of people getting quizzed on the prog chart or the surface analysis chart. Obviously in commercial, absolutely. In private, we all did. But instrument icing is the name of the weather game. So this is structural icing. There's another kind of icing called induction icing. And this is where icing prevents. Oh, you want to say what it is?
Yeah.
Go ahead.
This where our air intake takes in icing, and then we have issue.
Yeah, it's where the icing is preventing air from entering our cylinders. And we need three things to make combustion, right?
Air, fuel.
Spark, right? So so if we starve the engine of air, then we have no more combustion, no more thrust, no more engine. Yeah.
Is this a carburetor?
Yes.
One that's
Yes. So we can actually get carburetor icing even when we're not in visible moisture, right? This is actually something we also learn a lot in private. And right, we have a venturi, right? And so as the air flows through the carburetor, which has a venturi inside of it, it goes faster, lower pressure, lower temperature. You can actually have carburetor icing, even as high, I think the FAA manual says as high as like 70 degrees Fahrenheit. This is why if you fly an airplane with a carburetor that has carb heat, the descent checklist or the pre-landing checklist will be carb heat on. I got my private pilot in a Cessna 172 M model, Mike model. It's a 150 horsepower Lycoming engine carbureted, and it has carb heat. So the landing checklist was carb heat on. That was part of the checklist, even if it was 90 degrees out, because we just don't want to mess with the possibility of carb heat when I'm that close to the ground. And you obviously sacrifice a little bit of performance when you turn on the carb heat because it heats up the air, and that decreases the air density. So there's now less air molecules going into your combustion. But I'd rather have less power than no power. So that's what happens there. Same with our fuel system. You know how we have that breakaway valve. We'll talk more about systems next week. We have that breakaway valve that in case the fuel filter gets clogged, It'll allow the fuel to flow around the fuel filter. Same concept here, right? I'd rather have dirty fuel in my engine and some engine than no fuel in the engine, and it stops. So induction icing, let's talk about where it could form in addition to the carburetor. That's very common.
System and fuel, like.
Yeah.
checked in them.
Yeah.
Wouldn't all of the fuel be already clean? Cause isn't 20 gallons going to our fuel? Like, system like every hour?
Yeah, in theory, yeah. That's why I think the system is designed how it is, right? I think the idea there is that something, if it's just over time, the fuel filter is so clogged, or maybe it was cleaning out, maybe we got really dirty fuel and so now it's clogged. Maybe that's what happened. I have actually not heard, we should ask around, never heard of this. I never hear about like, oh, the fuel filter got clogged and that's why there was an accident. Heard of that? Maybe it's because the system is designed with the breakaway valve. I've heard a lot of other causes of accidents, but not. I don't know if it's very common. Let's come back to induction icing. Where does the air come in for our cylinders, right? Right here at the nose,
The nostril.
the nostrils, right? Well, guess what? That is kind of a thin area, right? And it's right in the airstream. So you could actually have icing that blocks the nostrils. Induction icing. Yes.
Isn't air intake on the right side?
Oh, sorry. Yes, it is on the right side. That's for cooling. That's for cooling. You're
Yeah,
right.
yeah.
I stand corrected, Moon. Thank you. So it's on the right side. That's an even smaller little hole.
Yeah.
You can just ice that sucker over, right? You can just ice that sucker over. No air coming in or reduced air coming in, reduced power, higher angle of attack. See, we're back to the basic aerodynamics again. Stall spin. Stall. Whatever. That would be an example of induction icing. Yeah. Carbon icing, carburetor would be induction icing, literally freezing over where the air comes into the engine. Those would be good examples. Cool. Let's talk for a minute about the different types of icing. Or do you have a question before we move on?
Yes.
Go.
Maybe it's some system related.
Yeah.
Naturally aspirated engine more vulnerable, or would be with the turbocharged or supercharged engine would be more vulnerable.
So induction icing?
Yeah. Or does it matter?
I don't know for sure, but I'm sort of deducing in my mind that I'm not sure there's a difference because they both require air. And if the place where the air is coming in is what's icing over,
Yeah.
I don't think there's a difference in that part of the system between a turbocharged engine and a normally aspirated engine. I think.
I think on the turbo it should be worse. Because of the turbo.
A turbo engine or a turbine engine?
Oh,
We're talking about two different things here. So a
I-
turbocharged engine uses
yeah, the turbo.
turbocharged engine uses well, there's a couple of kinds. There's supercharged engines and turbocharged engines, right? But the concept is the same. You're harnessing exhaust gas pressure to push more air into the cylinders, which increases the amount of air molecules in there, which allows you to get better performance at higher altitudes. Versus normally aspirated, well, however much the pressure is outside, that's how much air molecules are going into our engine. That's what we have. That's why we have a service ceiling of 12,000 feet, right? Because above that, the air is just too not dense, it's too thin for there to be enough air molecules in our rotax for it to produce enough power for us to do straight and level flight.
So I said turbine.
You said turbo.
Turbo, yeah.
Yeah, turbo. Turbine is where instead of it being like compression, like a piston engine, there's a series of compressor blades that spin and compress, and then it works differently than our traditional piston engine.
Yeah. The reason why I asked.
Yeah.
Because of the structure. Yeah, I think of it as they're kind of sucking air from the outside and ram into it.
Yeah.
Which would you say that's kind of bad?
Well, they're not sucking air from the outside. Turbo systems suck air or use the air from the exhaust system, which is hot.
I thought that's how they spin.
That's how they spin.
Yeah.
So the way turbo produces that extra pressure to put more air pressure into the cylinders is by harnessing the exhaust gases, right? The speed of the exhaust gases. It's still pulling in fresh air for the actual combustion the same way our engine does. So that's why I think they're both susceptible to it, because they still both need that tube Somehow air's got to get into the engine
Makes sense.
from the outside.
Okay.
Yeah.
That makes sense.
We could do a little more research on that, but I have not read anywhere that says that turbocharged engines are less susceptible. It may be, but I don't think that was in the handbook.
Okay.
There's always more to learn.
Yes.
Okay, let's talk about the different kinds of icing. Okay, so there's 3 different kinds of, well, 2 really, but a mix of the 2
Kind.
types of icing. Types of icing. Different types. No, I'm talking about now. Okay, so this is like 2 sort of like problems that ice can cause for us, right? It can form on the structure. It can form in a way that blocks induction.
So
Not instruments.
Here.
Yeah, clear and rime ice. We're talking about clear and rime ice. And mixed ice. Clear, rime, and mixed. Okay. The way that, and these have different qualities, and it's important for us to know about them because the different type of icing can help inform what might be happening with our airplane and what we can expect while we're in icing. Clear ice, and whether or not icing is clear or rime, in part or mixed, has to do with how quickly the water freezes as it reaches the surface that it's freezing. So clear icing happens when bigger droplets, or we're going slowly, and the water freezes more slowly as it hits the surface of the airplane. So imagine we're going through a cloud and the water hits the leading edge of the wing, but it freezes kind of slowly. So it hits and then it kind of just gets pushed backwards along the surface of the wing by the airflow, and it freezes as it's being pushed back. Because it's freezing relatively slowly, it has time to move back, and it also has time for all of the air that's inside that water molecule to leave it. So what ends up happening is you have a clear sheet of ice that's nice and smooth, and it can also then go backwards behind, cover the surface of the wing. Clear icing. Hits and freezes slowly. So it moves back and it's clear because all of the air has left it as it freezes slowly.
That's typically bigger.
Bigger, or we're moving slower, but bigger molecules freeze more slowly. Sorry, bigger drops freeze more slowly. So that's in part why they would have more likelihood of creating clear ice. Rime is the opposite. Rime, maybe a small droplet, we're going fast, it freezes real fast on contact. So it does not have time to go along the backside of the wing. It is more chunky and milky and more on the leading surfaces. So why is it milky? Freezes quickly, and so it captures the air, little air bubbles that are inside there, and freezes them inside. So that's what creates the milky look. It is rough. So the clear ice is smooth, the rime ice is rough. Let's see if we can get some pictures going here. Then the next round we'll have pictures in the deck. Do this. You're right. These are 2 types of structural. They're most important in structural icing, right? Induction icing is all about, is the ice forming in a place where it's going to starve my engine of the air it needs to do combustion? So in that case, I don't think we really care if it's clear or rime. We just care, is it blocking my carburetor? Is it blocking my air intake? Those are the things that I care. Someone claimed that there can be fuel icing. We're not going to talk about that today because I don't know if that's how common of a thing that is. Maybe you can talk about that in your double eye check ride, but for the instrument, the most important things are carburetor ice for induction, carburetor, and like the actual air intake. Okay, let's get some types of ice accretions here. Oh, this is from NASA. Great. Where was that? View picture. Why is it just taking me here? Is it somewhere on this page? There it was.
NASA's used for flight too.
Oh yeah. Even the military uses ForeFlight. Everybody's on ForeFlight. Okay, this is not the best picture, so let's find a different one. Yeah. Yeah.
Jacob can give us a
That.
great answer.
Oh, really?
He's a bartender.
Oh, you know all about ice. He hates ice. We all hate ice at instrument flying. That's true.
I'm more of like a flavor type.
Okay, all right, good. I got it. Got you. Yeah, the lavender ice, the
Yeah.
cherry ice. Okay. Okay. Yeah.
Like how minerally it is and how much like
Oh, wow.
that affects your drink when you shake it too.
Whoa, I didn't know about that.
Oh.
I did watch a YouTube once about like how they make the very, very clear, like shaped ices, ice for like bars, like fancy bars, like the sphere ones that are like, how do you make it like perfectly clear? That was a good 20 minutes of my life. I'm into it. Into it.
I think that one, I might have watched similar video.
Yeah,
That one is explaining the difference between clear.
basically, right? Right, but in your drink instead of on your. Okay, this is a NASA site, so I think we can trust this. Here's the beginning of some ice formation on the leading edge. It's getting worse. Significant horn formation on the leading edge. Using pneumatic boots, which we're going to talk about anti-ice and de-ice in a second. Those are the boots. All right, so let's talk in. Oh, here we go. Type of ice, rime, severity, light. See how milky it is? Type of ice, rime, severity, moderate. It's super white. It looks like snow. What's the top? Clear ice? Let's see. Okay, yeah. Clear ice, severity, light. So they still have little horns, but see how in between here it's totally clear? Severe. This is clear ice, moderate. Clear ice, severe. Extensive coverage on lower surface. But not the same on the leading edge, right? Like it's still pretty clear on the leading edge compared to the rime down here. Oh, this is mixed. That's the third type, which is a little clearer and a little rime. Translucent stagnation area. And then here's the mixed moderate. And then here's the rime. Okay. I can drop this in the chat so you can take a look at these pictures on your own later. But this is the different types of icing. Yes.
Question.
Yes.
For us.
Yeah.
I mean, not us, but as a pilot.
Yeah.
Would clear ice more vulnerable in the lower altitude and the rime ice in the higher altitude?
I don't know. I wonder. I don't know. Tell us your thinking on why that might be.
Because the higher you go up, the colder it's gonna get.
So
So
interesting.
I think rime ice, the instant freeze would be more likely happen.
Could be.
But the one thing I can't clear it is you said clear ice is a bigger molecule.
Like drop.
Yeah,
Yeah.
I'm not sure if the lower altitude has a bigger or smaller drops. I'm not sure what
Or
determines.
it may not. I don't know if the altitude has any determining factor on the size of the drops. I don't know.
Maybe just the moisture of the clouds.
Yeah. Which will get us into in a let's talk about it now. There's such a thing as called super. You're getting into a concept of icing, which is like some clouds are just have more moisture than others, right?
Yeah.
You can fly through a little wispy, hazy cloud and it's not that much moisture in it. But like a thunderstorm, like a cumulonimbus is full of water. Those are going to have huge drops. So there's this thing called a supercooled liquid droplet, which is a big water droplet that's very close to or even almost freezing itself. That's going to be probably most likely to create our clear ice situation. Yeah, but we're going to get ice the fastest. This is using the word accretion. Did you see that? Accretion is a word that means how quickly ice forms on a surface. So we got super cooled liquid droplets. They're big, very cold liquid droplets. The ice is going to accrete or form on our surfaces faster than if we're in a cloud with less moisture or smaller droplets. So those are called supercooled SLD, supercooled liquid droplets. We're going to see that in our weather charts. That's going to be like what you should think when you think of SLE, supercooled liquid droplets. A lot of ice real fast. That's what's happening there. A lot of ice real fast.
Okay.
But they're freezing slowly.
Because they're big. They're forming the ice slowly because they're big.
So if DP were to ask you, what determines clear ice or rime ice, you would answer the moisture.
The speed at which the droplet freezes, which is related to the size of the droplet. But if it has time to be pushed back and form that nice clear layer as it freezes, it also has time then for the air to leave, clear ice. If it freezes instantly on contact, it's capturing all that air in there. It's being all rough. It didn't have time to freeze as it got pushed back. Rime. Mixed, a little bit of both.
Right, but more realistically,
Yeah.
like DPE gives you kind of weather.
Yeah.
Oh, what kind of ice can you expect with, I don't know what.
I don't know a way to predict that.
Okay,
Icing, yes or no. Type of icing, the only way we know is through a PIREP.
oh, okay, okay.
But in terms of our charts or the weather, I don't even know if NASA knows really, or NOAA or the National Weather Service can predict clear, rime, or mixed. We would know from a PIREP.
Definition for the temperature for the clear rime and mix.
Is there? Where you're more likely to get one or the other?
I think so.
I would believe you. This is why we need actual updated slides, right? And it's also why you should read. There's an icing section, not only in the PHAC, but there's also an icing section in the instrument flying handbook. And in the emergency section, especially of the instrument flying handbook. What do you do when you encounter icing inadvertently? Yeah. If you have that pulled up, I would love to know. But
I just
otherwise
remember.
we'll put a sticky note on that. Wayne says, and we'll believe him, that it may also have to do with the temperature. Actually, that makes sense, right? Because if it's colder, it's going to freeze faster. So maybe that's why it's more likely for rime. I'm now hypothesizing. We'll need to double
I
check.
think so, yeah.
That would make sense intellectually. Now that you say it, yeah. Cool. Let's talk about now ways that our airplane might be equipped to handle ice, because it's not like, oh well, now we're gonna get icing, we can't go anywhere. Otherwise, none of us would ever have gotten here from Fargo to California. So there's a couple of different systems. Get a color going here. We've got anti-ice and de-ice. Anybody want to tell us the difference between the two?
TRS is a method that you do so that you won't get ice in the beginning.
Correct.
And then de-icing is the fact that you already have ice and
Yes.
you get it removed.
Correct. It has to do with whether or not you're preventing ice from starting in the first place, or you're getting rid of ice that's there. Exactly. So we have a number of different systems that are anti-ice and or de-ice. Some of them can be both. So what's the only anti-icing or de-icing system we have on a sling? Pitot heat. That's it, right? The little heater inside the pitot tube. There's an argument about whether or not that's anti-ice or de-ice. This came up in my CFII check ride. The DPE was like, is the pitot heat? He asked me the same question. What anti-ice and de-ice equipment do we have in the sling? I said pitot heat. He said, is it anti-ice or de-ice? I said it's both. And he was like,
Sure about that?
really? Really? And I said, yeah. And he said, you ever turned on the pitot heat in the sling? And I was like, yeah. He said, how hot did it get? I was like, medium hot. He's like, exactly. According to this DPE, he was making the argument that it was more anti-ice than de-ice. He was saying if you already got a thick layer of ice forming, he doesn't think that our pitot heater is going to be strong enough to melt the ice. I think that's in the category of DPEs. Obviously, I still got the cert, right? But like, that was his opinion. I think you could make an argument that pitot heat is both anti-ice and de-ice. There's also some difference of opinion. You should always follow whatever's in the airplane flying your POH for the aircraft, right? For all your anti-ice and de-ice equipment. Our POH is silent on this because they just say don't go into icing conditions. Our airplane is not approved for flight into known icing. But some people with pitot heat and an IFR approved airplane, they'll just always turn it on before they go into a cloud. That, hey, turn it on, like, then I don't have to worry about it. Some people only turn it on if they're like within like 10 degrees of freezing, something like
So
that.
our plane, if we go to Canada, we can
Yeah.
fly into the clouds.
Is that true?
No, I'm just.
You're asking?
Yeah.
I don't know. I don't know what the Canadian light sport rules are. I also don't know if maybe because it's an American registered plane, if they would say like, oh, you need to follow the limitations that were put on you.
I'm just curious,
Like a
if you're illegal to fly clouds in other countries.
The sling is fully equipped, right? Like it is actually probably better equipped than most of the other GA aircraft on this ramp to fly into IMC. I mean, look at all this glass, right? Like look at the amazing navigator we have. Look at the G3X we have. We have pitot heat. Still probably not, it's definitely not approved to fly into known icing, but into clouds for sure. If we re-register it in South Africa, probably it can go into IMC. And I hope that the regulations will change. It's just regulatory, right? Light sport can't go into IMC. We hope that that will change soon. The regulatory limitation, not a technological or systems limitation. Is that kind of what you're getting at?
Yeah, I'm just curious if we could fly into known icing or clouds in South Africa when we know.
Known icing, no, because we don't have enough. The plane is not approved for flight into known icing, period. The pitot heat is just there just like in case you accidentally do. But flight into IMC in other places, I don't know for sure, but I would imagine yes. Like it's a very, very well equipped aircraft for IFR flight. Yeah. Let's talk about a couple other anti-ice and de-ice types of systems, okay? One kind of anti-ice system is called a TKS system or a weeping wing sometimes. This is a system where there are little holes in the leading edge of the wing and the tailplane that weep out, like dribble out a glycol solution that lowers the freezing temperature of water. Those of you who live in snowy places, you know, like when it snows, they salt the road in order to prevent ice. It's the same concept, right? That salt dissolves in the water, lowering the melting temperature because physics, right? So this glycol solution that gets kind of dribbled out, it coats the leading edges, it coats the wing, and it lowers the freezing temperature such that ice does not form. It's an anti-ice system. It's got some nice advantages, right? Because it's a weeping wing, it protects not only the leading edge, but also the surfaces of the wing. It has some disadvantages. Well, the little holes can get clogged. You could run out of fluid. The fluid is heavy, so there's a weight penalty. Those systems need maintenance because, you know, you're flying through and a bug is going to clog it up. So there are pros and cons to like a weeping wing or TK. TKS, I think, is the brand name of this kind of system, of a weeping wing system. That can also protect your propeller, by the way. You put a little, because the propeller also can get ice on it. It's like a rotating wing out there, right? An airfoil. You like put a little bit of fluid at the propeller base. Centrifugal force will pull that fluid along the whole length of the propeller and protect it.
What does that mean for like the lift of the wing? There's a bunch of little holes in it.
I don't know if there's a huge penalty. There's probably some penalty. I don't think it's that big. I haven't heard of like an aerodynamic penalty as one of the major cons of a weeping wing system, TKS. It's mostly the other things. Holes get clogged, you run out of fluid, fluid's heavy. It requires maintenance. I guess they get clogged and requires maintenance or similar.
That's not the pneumatic boot?
No, but we're gonna talk about that next. Another kind is called this is now a de-ice, is a pneumatic boot.
Is that just like a flicker?
I'm gonna show you a picture of it in a second. Is that how you spell pneumatic? I think so. The silent P's always get me.
Yeah.
Pneumatic boot is actually what we're looking at here on these NASA pictures, where there is a part of the wing. See this black part of the wing? This is actually kind of a rubberized piece, and we can actually inflate this rubberized piece. We can kind of put air behind it to inflate it for a moment, and then take the air out, and it'll kind of suck back to where it, be back to its normal position on the wing. Pneumatic, meaning we're going to fill it with air, blow it up like a little balloon, and then release the air. What this does is it breaks the ice apart that is formed there. So you can actually see, I think what's happening in these is that this part of the pneumatic boot has been disabled, and this part on the other side of the measuring tool has been enabled. I think that's what's happening here. Yeah, okay, so this is the active boot on both sides, and then they've deactivated it here in the middle. So what you do is as ice accumulates, you activate the pneumatic boot, it expands, and as it expands, it cracks the ice away, and then the airstream moves it away. Then it reduces, goes back, more ice forms. Oh, no problem. Expand it again, crack the ice, goes away. So sometimes you actually need to cycle these a couple of times in order to crack all the ice. Advantages. It's cheap, right? It doesn't require as much maintenance. There's no weight penalty for all the fluid you have to bring. Disadvantages. It does require a little bit more active participation of the pilots to decide when and how often to activate it. Whereas we being when you just turn on and the fluid's going. And relatedly, one of the major cons to the pneumatic boot system is a concept called a risk called bridging. So say you have some ice forming like on these pictures, and you activate the boot. While the boot is inflated, more ice forms while the boot is inflated. And then when the boot is deflated, you now have a bridge of ice in the shape of the inflated boot. So I'm doing this with my hands. We can probably find images on the internet here too, right? But like, this is the ice, okay? So ice hits the wing, my pneumatic boot expands, breaks off that initial ice, like it's supposed to. Now, while it's still inflated, more ice forms in the shape of the inflated boot, such that when now I'm gonna deflate my pneumatic boot, I have this layer of ice that is still out there beyond the reach, you could think of it, beyond the reach of my fully inflated pneumatic boot.
But wouldn't that just be like a thin layer?
Yeah, and this is why you still use pneumatic boots, because, and actually the FAA has done a bunch of studies, and probably NASA too, where like the risk of this is actually not as high. If you use your pneumatic boot per the instructions, this is not a catastrophic risk, but it is a risk. It can happen. But it you know, like you're to your point, Chris, like really? I mean, yeah, it can. We need to be aware of it. This is one of the major limitations of a pneumatic boot system, bridging. Then once there's that layer of ice beyond the reach of the inflated boot, now more ice is forming in front of that, and we have no more de-ice system.
Well, that happens when you just like change your pitch.
What would happen? Sorry.
When bridging happens. You just, like,
Bridging can happen at any attitude. It has to do with, I think, the atmospheric conditions, also how long the pneumatic boot is inflated, right? The longer you leave it inflated, the more time there is for that ice to form. Also has to do with, I think, probably the severity of icing, right? How quickly you're getting icing. All of that, I think, comes into play for the risk of bridging. Cool. There are some other types of anti-ice and de-ice. One is, there's my red marker. A system that I would call both anti-ice and de-ice would be sort of like a bleed air system, or just I forget what it's called, but basically like both of these use heat to heat the leading edges and your propeller and other critical components. So that could be drawn from bleed air, meaning like some of that exhaust gas air that's hot that they send through little channels underneath, right, the surface of your leading edges to warm the surface. Similar, it's the same concept as pitot heat, right? Just warm it up. That'll get rid of the ice and it'll prevent ice from forming. Or it could be electric, right? Like you put, same as our pitot heat, except now you're putting those heating elements along the leading edge. That could be anti-ice and de-ice.
Send hot air via electric or
from the engines. Bleed air from the engines.
Kind of like cabin heat, but outside.
What's that?
Kind of like cabin heat, you're
Yeah. Yeah, exactly. However, when I say heater, it wouldn't necessarily be hot air. It would be like, you know how you have like the rear defroster in your car has those like little lines on it, and so those like little lines you have, it'd be the same concept. Yeah.
And it doesn't weigh that much. So it doesn't.
Potentially, right? It weighs less than like a TKS system. Potentially, it might be able to handle more ice right? Or thicker or more severe icing than some of those systems. All anti-ice and de-ice systems have limitations, right? There's always limitations, but trade-offs between the different kinds of anti-ice and de-ice.
Slings, we don't have any de-icing systems.
Unless you consider the pitot heat.
But this is
Right. That's Moon?
Are we done with the anti-ice? And
Yeah, yeah.
Okay. I found the definition of the clear.
Tell us, please.
As Wade said, or unlike Wade said, there's no definition of the temperature.
Yeah,
However, the clear ice says temperature close to the freezing point, large amount of liquid water,
yeah.
high aircraft velocity, and large droplets are conductive to the formation of clear ice.
This makes sense. You're moving fast, so it freezes as it travels backwards. Big droplets slowly freezes as it travels backwards. What was the third thing? Or were there one of those two?
The first thing was the close to freezing.
Oh, close to freezing point. Okay, got it. Okay, got it. Because they're not already super cooled, so they're gonna take more time to freeze. Cool. I like that.
And the rime ice
Yeah.
says low temperature.
Sure.
So I'm assuming below freezing.
Could even be below freezing potentially. Yep.
Lesser amount of liquid water.
Okay.
Small
droplets.
Low velocities.
Yep.
And small droplets are conductive to formation of rime.
So this tracks. This tracks, right? It's all about how quickly the droplets freeze, whether it's going to be clear, rime, or mixed. Yeah. Let's talk about recovery from inadvertent encounters with icing. First thing we're gonna do, Chris, you tell us. We're coming back to the note that I was like, let's not forget to talk about this. If you inadvertently encounter icing, either that's exceeding your limitations from your anti-ice and de-ice, or you're in a plane that's not approved for flight into known icing, what's the first thing you do?
turn off autopilot.
Turn off autopilot. Why?
Because you set it to 3,000 feet,
Yeah.
it's gonna want to climb.
Yeah.
But if you have ice, there's gonna be weight to it, so it's gonna always it's gonna fall drop in altitude, so it's gonna always think, oh, I gotta climb, and then it's gonna increase your angle of attack, and then you get stopped.
Exactly, right? Our autopilots, and I think most autopilots in general aviation aircraft, they don't have flight envelope protections, meaning it is not connected to our angle of attack sensor. It has no idea what's happening with our angle of attack. So it cannot protect us from a stall. In fact, it will just stall you. It does not give a shit, right? It's like, oh, you wanted 3,090 knots? Here you go. Here you go. This is the angle of attack that's required. Sorry, we have a very sophisticated autopilot that does not have flight envelope protections. What's that? Yeah, exactly. Yeah, you say jump, I say how high. That's the autopilot. Bigger jets like the Airbus, for example, they have flight envelope protections to help prevent this. But in our case, first thing, autopilot off. Also, I want to be able to feel for myself. What's the trim doing? Am I already full trim back? Am I full trim back and I'm having that back pressure? That's a pretty bad situation, right? But mostly it's because the autopilot will stall you and you will have probably very little, well, I guess in theory, your AOA should start beeping, but we want to be able to prevent that before we get to that point.
Our trim is not connected to our autopilot.
It is. That's how the autopilot controls our edge. Their trim. Yes. And servos in the elevator. We're gonna have to double check that. I don't know if it's trim and the elevator or just the trim. I don't know.
The trim.
Disconnect. That's right. Yep. So first, turn off the autopilot. 2, reduce the angle of attack. Reduce your angle of attack. For all the reasons we've just talked about. Yeah.
Autopilot.
Yeah.
Not on altitude.
Just on heading mode?
Yeah.
And
Just
you're
like
controlling the
slowly.
pitch. Well, so then you're controlling the pitch and it's controlling the heading, is what you're saying?
Yeah, so we just have it on heading,
And nothing on altitude.
nothing on altitude.
I guess you could, but it's hard to fly that way because when you're controlling the stick, right, you're probably gonna, or there's turbulence, you're gonna bump it and then it's gonna disconnect. I would say just turn it off. Also, if you do stall and you enter an uncoordinated spin, you know, when you're in a spin, you want immediately full control, not have to wait for the autopilot to disconnect.
I didn't know you could do one, just like one thing.
It's not common practice, unless, I don't know, do you do it? Do you find cases where you're flying with only one axis autopilot on?
Use, so it's asking for.
Yeah, no, I can't really think of situations where I use the autopilot on only one axis. Typically, it's both.
I don't even know if you do that, you just have nothing but good altitude.
Maybe it's not even possible to.
Yeah, I can't imagine.
I've never done it. Yeah.
You can do just, I think, altitude, but you only do.
We'd have to explore this a little bit. This is why we need slides. We're doing the best. We're crowdsourcing this today, but
You
I
need
think
a
Wayne-
template to
I
test
or we just need to read the whole GFC 750, you know, our whole autopilot manual, which there is a supplement for that. But I think Wayne, I think the answer is like just turn it off. Just turn it off. Yeah, hand fly. Number 2, reduce the angle of attack for all the reasons we've said, right? We know that we're having higher weight. We know that we're having disrupted airflow over our wings, less lift. Decreasing the angle of attack keeps us safe by requiring less of the wings, getting us further from our critical angle of attack, further from a stall. And then 3, get out of the icing. What are some options for getting out of the icing? Descend. Typically, it's going to be warmer below us than above us. What's another option for getting out of the icing? Okay, so what would I do?
So
This is actually a private pilot question. What do we do? What do we learn in private pilot when we're doing our 3 hours of simulated instrument? Oops, I flew into a cloud.
yeah,
Ride on your instruments, and then do I turn? That's it, right? I know there was no cloud behind me. Turn around. That could be another option. Any other ideas for how to get out of icing?
Let's say you're like in the break.
Yeah.
Or flag see it's no. Or you could look at like METARs of airports that are near you to see where it's clear.
Possible, sure. I like the idea. I like the idea of where you're going.
and you, if the ceiling of the cloud is not that high, can you just go above it?
You would go, if you go out of it, you're not getting any more icing. But the icing you have might still be there because if the exterior temperature is still freezing, right? That's better than nothing, right? At least you're not going to get more ice. But what do you need in order to climb? Higher angle of attack, more lift. We already know that we're getting, you know, our margins are reduced. Not impossible. You catch it early. I like the idea of descend and turn around. Couple things to keep in mind. Turn very gently. Turn very gently, right? When we turn, we sacrifice some of our vertical component of lift for horizontal component, which increases our load factor, increases our stall speed. So this is not going to be a kind of thing where I'm doing an emergency steep turn to get out of icing, right? That is probably going to be deadly. We're just going to be a nice, chill, very shallow bank turn around.
Flight?
Not slow flight, because we want to be, you actually want to increase your airspeed.
No, like the slope. Like,
Oh, yeah, exactly, right? Like maybe you put in 10 degrees of bank or something. Very chill turning on. Is this an emergency if I get into icing in a plane that is not rated for flight into known icing? Is that an emergency?
I think you see that. Like if you were a student and you had icing, probably because you're like inexperienced. But if you're like a PPO and you have like hours, you'd be like, just go.
So your thinking is, I like where you're thinking because you're thinking about personal minimums, right?
Yeah.
You're thinking about, are there certain hazards that are less hazardous to me because of my inexperience or my experience? That's a good way to think.
Because if you're like a student pilot and then you think it's an emergency and then you put 7700 and then 121 and then you land and they're like, why did you do it? Or like icing, okay, but you landed and now you don't have icing and you made me do all this maneuvering just to.
They're not gonna care. They're not gonna care. Never hesitate to declare an emergency. Never hesitate to declare an emergency. That's not a thing. I think people think about that. What that really is like their shame reaction, and they're worried about being ashamed that they like did something wrong. Don't worry about that. Like, get on the ground safely. Everybody's gonna be happy to do the extra work to keep you safe, rather than you not asking for what you need and not coming home, right? Don't worry about that. So I think you're right, Chris, in that there's whenever we do hazard mitigation or decide is this emergency or not, part of what we're thinking about are our own experience and limitations. However, I'm going to go with your answer, Erica. Always, if you're in an aircraft that is not approved for flight and icing and you're in icing, that is always an emergency. Always an emergency. Even if you're a 20,000 hour ATP rated pilot, that is always an emergency. Because this can happen, especially if you're in a cloud with a lot of icing, right? If you're getting ice accretion really quickly, this could be a 30-second to disaster, right? This can happen. This could be fast. This is not, and that's why, Jacob, I kind of like where you were going too, because you're thinking about the weather, but we don't really have time in icing to be looking at METARs and other things. We really just want to be autopilot off, reduce angle of attack, get out, descend, turn around, declare the emergency. We can ask, what I might recommend is instead of going on ForeFlight, when I declare the emergency, do you have anything on the radar? Do you have any suggestions for a heading of where I might be out of icing? Ask them, make them do the work. You got to control the airplane now. Aviate, navigate, communicate. Yeah. Cool. Last thing on, there are two last things on icing. One is how do we know in our flight planning if there's gonna be icing? And the other is I want to close with the reg and make sure we're all up to speed on the regulations on this.
There's a reg for icing.
Oh, there are multiple regs. It's the FAA, Chris. There's so many regs. The question you should be asking is, do I have it memorized? The answer is no.
No.
I have to look that up. But there's one reg in particular I want us to be looking at. Let's start though with how do we know if there's going to be icing? What are some ways to know?
Pirate.
I love that. Okay, let's see. Colors? Nope, I still have blue. One, Pyrex. This is the only way to know what kind of icing is going to happen. Actual icing Pyrex. What's another way to know if there's going to be icing? Or,
Airman?
yeah, exactly. For icing.
Which is, would it be Zulu?
Yes. Right? Tango's for turbulence.
Yes.
Sierra is for like visibility. No, but maybe they also. Sorry.
Zulu's next.
Zulu's icing? Okay, good. What? Slots. Okay. Airmets, Pyreps. And then we're gonna look at all of our like imagery weather charts. I think we might have gone through this in a high level last week, but I just want to do this one more time to look at the charts that will help us predict whether or not there's going to be icing. 2 ingredients for icing. What are they? Just as a review.
Freezing temperature.
And cool. So the first thing I'm going to do is I'm going to go to products icing. Tools icing? No. Weather icing? Weather icing. And this is now going to default to one of our weather of our icing maps. You also have all this in ForeFlight, by the way. The first thing I'm going to do is I'm going to click on a hamburger. And you see up here, it has a little drop down, the kind of icing chart we're going to look at. I'm going to look at freezing level.
Damn.
Correct. So this is telling us, turn off the airmets and the sigmets for a second. This is telling us the freezing level, where freezing starts, exactly, where freezing starts by color coded. So down here, we're in this like red, I can open the legend. Freezing level is somewhere between 15,000 and 17,000, flight level 150 and 170. 15,000 and 17,000 approximately, right?
Oh, so that kind of makes sense. Like in Texas is higher because Texas is usually hot.
Yeah, and we can just tell like today, this is where the freezing levels are. Yep. So, if I'm planning my cross country and I look at the freezing levels and the freezing level is way above where I'm planning to be, I don't even look at it in their charts. There's no icing. I can go through as many clouds as I want, right? Now, if it's close, add some margin of error. Here's the other thing though, and this can trip people up in their check rides. So don't do this common error. Don't look at the freezing chart and be like, oh yeah, I'm planning a flight from Seattle to Boise and I'm going to be at flight level 250. Which now I'm above the freezing levels, right? If I look down here. So yeah, there's definitely going to be icing. No, we only now have one of the 2 ingredients, right? Don't make that mistake. Don't look at the freezing chart and tell the TPE, oh yeah, there's going to be icing. You only now have one of the 2 ingredients.
So
for the temperature.
This is just for temperature. This is just for temperature.
I was just gonna ask that, like, which one does this chart give you?
This is just the freezing level. This is just temperature.
So now you gotta look at visible.
Exactly. So now we need to figure out the other ingredient. Okay. So one way I can look at that is the cloud forecast, but the FAA, the Aviation Weather Center has made it even easier for us by giving us a couple of other charts. There's one called icing probability. This is the one I want to look at next. Okay. Icing probability. This is based on altitude, right? There's different probability of icing at different altitudes. So I'm going to set this for, I don't know, 9,000. You'll notice a couple of things. There's this little sort of tannish color, and you'll see the legend says that means that there's terrain there. So those are the Rocky Mountains above 9,000. If I go to 6,000, you'll see the Rocky Mountains better, right? If I go to 3,000, now this, so any of that is terrain that's 3,000 or high. Obviously, you're not going to be flying there, so they just block it out, right? If you're going to be at 3,000, you're not there because there's terrain. But let's say we're going at 9,000. This will now show me the likelihood, the icing probability in percentage, okay? So this is taking into account freezing level and visible moisture for us. It does that both, and it tells us the percentage likelihood. So up, go ahead.
On this one, this chart alone that we're looking at is sufficient enough to tell the DPA, hey, we're not gonna get icing where we're going? Or do you want us, like?
You should be proficient in all of these charts.
So, so
You
check
should be
out-
proficient in all of them, yes. If you looked at this and you were like, yeah, there's less than 5%. Look, white is not 0%. It means less than 5%. So as long as you tell the DPE, okay, there's less than 5% chance, fine. But then the DPE is going to be like, is there 0 chance? Well, let me check my freezing levels. Because if I know that I'm not near freezing, yeah, there's 0 chance. Let's go a little higher just for funsies here, right? As we get higher, you'll notice that the probability of icing increases. The temperature is decreasing, right? And maybe there's also higher clouds. But if I'm going at flight level 180, you can see down here in Arizona, we actually have some pretty high probability of icing at 18,000. So if I'm like going from Phoenix up here to Colorado Springs, I might be at 18,000. I'm flying right through that, and that looks like it's 65 to 75% chance of icing. So that means that if my airplane is not approved for flight into known icing, I cannot fly there. Unless my POH says approved for flight into areas of whatever, however severe icing, I cannot fly there.
Can you put the not the prog chart, where the pressures are, so we can see like why there's a.
Yeah, sure.
I see it. Oh, there's a lot of rain.
Visible moisture. Yep. Yep.
This might be a little out of topic.
Tell us.
Since you talked about terrain.
Yeah.
And where is the highest terrain in the entire United States?
Isn't it Mount Whitney? Not Mount Whitney. Mount Whitney's the highest in California.
I'm not sure. What state do you think?
Oh, I was gonna say either like Colorado. I think it was gonna be somewhere in the Rockies. No?
There's like.
It's somewhere in Minnesota.
So
I'm like home state pride. Oh, sure, that makes sense.
Yeah, the highest peak of California is a little higher than highest peak in Colorado.
Is that so? Okay.
Yeah, which
Is it
I
Mount
thought-
Whitney?
I'm not sure which one is.
Okay.
I peak in the youth.
Mount Whitney. Okay. Great. Okay, there you go.
Yeah, I thought the Rocky.
You should tell dispatch that, and they can write that on their fact of the day whiteboard now that they have that.
Fun fact.
It's fun fact of the day. So this is icing probability at different flight levels. Okay. You'll also note that this is also showing us some PIREPs. You'll see there's PIREP symbol. This little trident situation is the icing PIREP symbol. Down here. This is the icing. To me, they look like tridents, like King Triton, you know?
This shit from Guyana.
Yeah, sure. Exactly, right? So they also are color coded on aviation weather, and they have different number of little middle tridents based on the severity of the icing. So this green one is light icing, and it'll tell you the flight level at which it was reported. I can click on this and get all the details. including the type of aircraft. So this was a C-421, was that. Oh, a Cessna Golden Eagle. Looks like a light twin. Okay, so actually that's pretty relevant to us. Like if it was reporting icing, yeah, that's right. That's right. We want to know about that.
Oh, wow, that's pretty.
It's pretty high. This was the temperature was -7. The ice was light rime ice. Tells you the time, the type. Let's look at this one. This was also light. This was a type was BE9. Anybody know? Beechcraft 9.
Bonanza.
King Air. This is a King Air.
I thought it was like.
You're saying some serious icing in that VF in that IFR equipped aircraft. Exactly. This is a King Air. So you know it's got some anti-ice, it's got some de-ice, but it's not that much bigger than we are. This isn't a Boeing 737. Temperature was -8, ice trace to light, and they didn't tell us if it was clear, rime, or mixed. Let's look at another icing PIREP. Oh, here's a better one down in Texas. This was a type of SF-50. Anybody know what that is? Oh, Cirrus Vision Jet. Cool. One landed yesterday while I was on the taxiway. They looked so cool. So this is a Cirrus Vision Jet, so that's small, like us. Really, right? That's part of what we're looking at is like how big is this sucker? Temperature was -6. Icing was moderate rime between flight level 200 and 212. It's very precise flight levels.
20,000?
Yeah, to flight to 21,200. Remarks during climb. DURC, during climb. DURD, during descent. Makes sense, right? They're going to climb through and then they'll get through the clouds, no more icing. They've got their de-ice turned on, carry on.
What's the CH?
It stands for the center that produced this PIREP. So this is Houston Center. The Z, so like ZLA is LA Center, ZHU, I think it's OA, I think it's Oakland Center. There's a list in the AIM, the different center codes.
This is not relevant to icing.
Yeah,
Legend.
yeah.
What's the purpose of reporting no turbulence? Is it to like override a previous PIREP?
Or to say like maybe there was like a turbulence airmet and you want to say actually there wasn't. That would be the reason well, there are two reasons to get a negative turbulence PIREP. One is that, right? It's like, hey, there was there was an airmet out there for say moderate to turbulence. There was none. So I want to put a PIREP to let everybody know like there wasn't any. The other reason,
You're Chris, and you want to just file.
you want to practice talking to flight service, right? You want to practice talking to flight service. The only 2 times I've ever talked to them were to do this, just for practice, right? I want to give a PIREP, sky clear, negative turbulence. She was thrilled to talk to me. She was so happy to take the PIREP. It was amazing. Then it shows up in ForeFlight and you feel, it's my PIREP.
It's like he tells the base of the clouds, and I'm like, I'm so stressed out. Right
Yeah,
now.
you can say unable. You can say unable. This is actually something to note. In certain visibility and ceiling conditions, ATC is actually required to query you every hour or something. They're required to collect a PIREP proactively. Like I think when the airport's IFR or when there's certain weather conditions and a certain amount of time, I think it's at least once an hour they have to ask. You have an idea what the bases and tops are. If you're not able, you're like overwhelmed, like sorry, ask somebody else. Sorry, unable. That's fine. They'll just ask the next flight. They don't know that you're on a check ride, right? So you tell them like AV, navigate, communicate. Sorry, bro. No, somebody else.
Never asked, but during the check ride.
No, exactly. Of course they asked you during the check ride. Like, of course they did. Of course they did. Of course they did. Fortunately, PIREPs are in the ground portion of the private ACS, not in the flight portion. So, what did who'd you go with? With Dean, okay.
I saw
Okay. Oh, right.
So we just
Nice.
be stuck
Correct.
like this.
That's just continue.
Dude, like,
Yeah,
6 p.m. Like, okay.
we'll do this another day. So there's three main charts here, right, in terms of predicting icing. One was the freezing levels, we talked about that. Two is the probability. Now we're gonna go to the third one, which is the severity, okay? So this we would look at when we have some kind of probability. First is like, if we're gonna, so this is telling us if we get icing, how bad is it gonna be? I recommend you look at the one that says with SLD, super cooled liquid droplets, because that can be where you can pick up icing real fast. So this makes sense, right? This area of Texas has more severe icing. It was also had a higher probability of icing. But now it's telling us the severity. So if I pull up my legend now, light blue is trace, light, moderate, heavy. And then the red, or these like kind of magenta, is where there's risk of these super cooled liquid droplets. If we go back to that NASA, those NASA pictures, it was giving us examples of the difference between, like, here's the difference between moderate and light, for example. I'm sure there are written down definitions, but they are, I think, probably potentially a little subjective as well. But that's how we count the severity of icing. So you might have a plane that's approved for flight into known icing, but there's a limitation in your POH about the severity of the icing, right? So like a TKS system, for example, it only has so many holes. It only has so much liquid. The liquid can only reduce the freezing temperature of the water so much. So it might be approved for flight into light to moderate icing, for example. Pneumatic boot, same thing. There might be a limitation. Only approved for flight into known icing, light, moderate or less. Or if you're in a Boeing 737, approved for flight into heavy icing, something, right? Like that's, but there can be limitations on your anti-ice or de-ice systems, and that's where the severity also comes into play. Makes sense, right?
Yeah.
Cool. Last item on this, and I apologize, we did not have time to go into departures more, so we will either pick that up next Friday or on week 5. Are the regs. I just want to make sure you're familiar with the reg for this, which I'm looking up on the, we have a text chain for the folks who are like talking about improvements to the slides. There it is. This is 91.527. This is the regs on operating in icing conditions. First of all, alpha, if your plane has frost, ice, or snow on any part of it, right? The windshield, propeller, control surface, the engine, or any part of your pitot-static system, you may not take off without getting rid of it. Unless it's unfrost under the wing, if that's caused only by the cold fuel. Otherwise, you may not take off with ice on any of those surfaces.
And this is why the big planes get sprayed on by that before they take.
There's a de-icing fluid, which is also a glycol-based fluid that gets sprayed on before you take off to comply with 91.527 alpha. Yep. By the way, that fluid, depending on the kind, has a different amount of holdover time. So they start a timer. There's all these timers in the cockpit, right? They start a timer when the de-icing starts, and depending on the type of fluid and the amount of precipitation that's happening, determines how long that airplane can meet the requirements of 91.527 alpha. It might be 10 minutes, it might be 15 minutes. If it's really heavy snow, it might be 5 minutes, who knows, right? Because the glycol solution, that anti-ice solution, or de-ice solution rather, stays on the plane for a little bit. Anybody ever been in an airplane that's been de-iced? Commercial airplane?
Like airliners?
Yeah, like airliner.
Yeah.
I was gonna say the Minnesotan, yeah.
All the time.
Yeah, all the time. Like I have never personally experienced that. But I've seen videos and it's like some kind of colored liquid, and then as you take off, you can like watch it all kind of get like washed away by the airflow as you're taking off.
Wait, I thought you were in Boston for a long time.
1 year.
Only
It was
1 year.
it was a very quick grad program.
But there's no like you never took.
I was home during the it was winter break when we had the blizzard. I missed my blizzard in Boston. I missed my Boston blizzard. Never been in a plane that's had to be de-iced. Bravo, no pilot may fly under IFR into known or forecast light or moderate icing conditions or under VFR into known or light moderate conditions unless you have functioning de-ice or anti-ice equipment protecting the rotor blades, prop, windshield, wing, blah, 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 all the important parts of your aircraft. Unless the airplane has ice protection provisions that meet this other part of the federal aviation regulations, or the airplane meets transport category airplane type certifications, which include, right, in order to be certificated as a transport category aircraft, it needs to be able to go into all the icings.
What about cargo?
Those can be transport category airplanes.
Even
Right.
though it's just like mail?
Has nothing to do with what's inside, it has to do with the standards of which the aircraft is produced and the capabilities and limitations of the aircraft. Yeah, so those FedEx, you go work for FedEx, that's a Part 121 operator. You have to have an ATP cert for that, just because you're carrying packages. That's an airline transport pilot license for an airline transport category aircraft. Yep. Actually, I've heard people love working for UPS and FedEx. Like they pay well, and Martin, the DPE, he works for UPS. He's like a very senior 747 captain for UPS. Yeah. Charlie, except for an airplane that has ice protection provisions that meet the aforementioned provisions, so anti-ice or de-ice, or for those with transport category airplanes, which automatically, by virtue of being certificated as a transport category airplane, have anti-ice and de-ice, no pilot may fly an airplane into known or forecast icing conditions. So that means if your POH does not say approved for flight into known icing, you may not fly into known icing. So that means if you see on that probability chart, right, that you're gonna go into, oh, I closed it already. If you see on that probability chart,
You can
I can
click
open it
Control
again.
Hit T.
What? Oh, I just
No,
opened my
no,
last
you can-
one.
You can keep doing it.
But I think I didn't close it. I just went now to ECFR. Yeah, let me do this. Weather, it doesn't take long. Icing. Click this. Right, probability, right? If I'm going into where there's probable icing and my POH does not say approved for flight into known icing, I may not. That's why it's so important. That's why they're gonna check you on this on your check ride. Make sure you're aware of that. You know that you're not gonna do that. So now we're going into the clouds, so we have one of the two ingredients necessary for icing. And Delta, if current forecast or briefing information relied upon in the pilot and command indicate that forecast icing conditions that would otherwise prohibit the flight will not be encountered during the flight because of changed weather conditions since the forecast, the restrictions in paragraphs B and C based on forecast conditions do not apply. Let's read that slower. If current weather reports indicate that the forecast icing conditions that would otherwise prohibit flight will not be encountered. Okay, that's their way of saying you checked your icing probability and it said there was no chance. But you then go into icing or the forecast changes. What is this saying? Restrictions in B and C of this section based on forecast conditions do not apply. This is why we need slides. Right? Because no pilot may go into known icing. I think this is saying, all right, now we're gonna have Jimbo decode this for us, or an attorney. Anybody here an attorney? Sometimes you need to be an attorney to understand the federal aviation regulations. I think what this is saying is if you look at the forecast and it says there's not going to be known icing, that's good enough. Right? They're not going to bust you on this if you accidentally go into it, as long as you did your NW craft and you were diligent and you accidentally went into it, you're not going to get busted for it. I think that's what this is saying. The bottom line, the main thing, the main take home is unless your plane says approved for flight into known icing of this severity or less, then you cannot go. Sound good?
Makes sense.
Be careful of 9117 this weekend. Everybody know what 9117 is?
Alcohol and drugs.
Correct, Chris. Be safe. Don't violate 9117. Have a wonderful 4th of July. And I will see you back here on Monday at 7 a.m. Next week is see that one I have memorized. 9117. I will see you next week. Next week is Arcs, Holds, and Systems. So it'll be
I
fun.
was using that.
Oh, really?
Yeah.
Uh-huh. Oh, shoot. It's gonna be a 10. Let me do that. Good.
Jacob's bar.
Oh, totally new.
Absolutely. Just 8 hours bottle of throttle. Rocket fish. Let's see, who's here? Chris was here. Moon was here. Wayne was here. Erica was here. 1, 2, 3, 4. And Jacob.
Oh, right.
You're welcome. Thank you for coming. Pleasure having you in person. I try my best, Erica, on the Zoom. It's just, I don't have the right setup.
I'm worried.
I need like a better camera, like the experience on Zoom. I just need a better.
That's just.
It's better than nothing. I